oftentimes we have data that it's useful to find repeating patterns in and use those for some kind of analysis. It can be useful for resource scaling, error detection, user engagement, whatever. And so I've got some files here to plot out our data. They're not interesting. I'm not going to build them as part of this video, but I thought I'd kind of use them to show what some repeating data might look like. So if we run this and we look at our data, you'll see, we've got these repeating peaks and valleys, almost like a sine wave, where they're not exactly the same. There are variations in them, but you can just look at it and very clearly see that there are some patterns here. So what we want to do is build a really simple system to detect, at any given point where we are, find something historically that is similar, and kind of give us a window into what we might be able to expect in the near future. The way we're going to do this, I'm going to use a library that's called Stumpy. It's an open source project provided by TD Ameritrade. I think they use it for financial pattern recognition. And basically it implements an all pairs similarity algorithm. And I think there's different ways to do this. I think a lot of implementations use cosine similarity, where they project vectors of data out into n-dimensional space and then look at the angles between them. The smaller the angle is, the more similar the vectors are. And they use that to, recursively iterate over this data and find similar pairs. I'll link in the description the actual documentation that talks about the algorithms and the papers behind the research. It's probably out of the scope of this video. But what I do want to do here is put together a simple pattern recognizer that consists of getting data, cleaning the data, transforming the data, getting a window that we are interested in matching, and then finding a match to that window. So I think what I'm going to do here is I'm going to start with a file. Let's call it pattern finder. And in this file, we're going to define a couple of things that we'll need later. So we're going to say minutes per record. I'm going to set it to 15. The data that I've got here is collected in 15-minute increments. And so we're going to just assume that every record is 15 minutes apart. Actually, looking at this data, it looks like this data is collected hourly. So let's do minutes per record is 60. All right. And then we're going to get some data. So to do that, I've got a data repository here. It's got a function get file data. I'm just going to use this. It's not very interesting. All it does is open up the CSV file and return the rows. So I'm going to say from data repository, import get file data, right? And then down here we'll say our file data equals get file data, and we'll give it a path to our data, which is going to be up a directory, and then we're going to put in the name of it, semi-repeating data.csv. And this will give us our file data. Maybe just put in here a print statement, make sure that we are able to get our data, and then we'll just run this real quick to verify our results. Looks like we did get our data, and you'll see this is the first record out of that data set. One thing you'll notice here is that the value of the data, and these are arbitrary values, but you'll notice it's a string. For us to do any meaningful processing on this data, we're going to need to convert it into numeric data. And so we could do that inline here, but I generally like to create purpose-specific files for this. So what I'm going to do is I'm going to create something called transformer.py, and this is going to have a one of our dependencies is numpy. We're going to import numpy and then give it an alias, and this is just going to have a single function. We're going to define transform strings to floats, and then we'll give our input data and the float data index. And the float data index will be used to tell us, this is two-dimensional array data. It'll tell us which of the dimensions we want to convert to a float. And so I think what I'm going to do here is I'm going to take this data, I'm going to convert it to an NP array, so that we get some of the built-in functionality from NumPy that allows us to convert these things. So I'm going to say np.array. We will use our input data, and then that will give us the ability to pull these dimensions apart. So we will say label data equals np array, and we're going to say everything and along the 0th axis. And what that means is that it's going to take, we've got two dimensions, we've got 0 and 1 inside each element. It's going to take and split the data apart along the 0th index and make those our labels. And then you can actually see an example of that. We've done it here. We're going to do the same thing here. We're going to say our value data and value data. NP array, and again we're going to take all of them, but we're going to do it along the first index. And what we have now is we have two separate arrays split out into one-dimensional arrays, and the reason we're going to do that is I'm going to convert the value data to float values and then zip these back up and return them. And actually I can do that inline here, and we'll just say float. So now the value data is float data, and we will say our return value is zip label data and value data, and then we'll just return that. And we'll return the return value, and then back in our pattern finder, just for fun, and then actually I'm not sure I need this. We could make it more complicated, but I'm not going to do that. So I'm going to say from transformer import transformed, and now I'm going to say transformed data equals transform, and then I'm just going to input the file data, and then I'm going to print out the transformed data, the first element there, just to make sure that it did what we expected. Just real quick, on pattern finder dot py, and we'll see that now our data value is a float, which is great. So the next thing that we want to do is we want to actually go into the data and pull out a window that we are interested in. And so for that, I'm going to create something called extractor. And extractor is just going to take the data, and it is going to pull out a chunk of it that we want to use as a pattern to match against. So I'm going to say get data window. We will pass in our transformed data, just to be really explicit about which of the stages of data we want to pass in. We'll pass in the window size in minutes, and then we will pass in the minutes per record, and then we'll pass in the window minutes offset from end. And this just gives us enough information to say, hey, start at the end of our data and then go back a certain number of minutes, which will correlate to a certain number of records, and then take, whatever size chunk we want. And so what we're going to do is say, we have to know how many records we're going to take. So we take the, we're going to say the window record count is equal to the integer. And again, these are going to be, we want to make sure we get an integer here and not a float. So we're going to say the window size in minutes, and we're going to divide that by the minutes per record. And the reason we have to cast this to a float is, if we get any remainders or something, it could return a float value, and we really need, a round number. So this will just truncate any remainders. And then we need the window record start record offset. And the Windows start record offset is going to basically be the starting point, counting from the end and going backwards, that we want to use as the start of our window. And again, this needs to be an integer, so we'll say Windows minutes offset from end divided by minutes per record. And so I probably need an assignment operator here. So with the record count set and the start index set, basically we can go to a specific place within the data set and start extracting a window. And so the next thing we need is the start record index, and it'll need to be an int. We will take the length of the transformed data, and then subtract the Windows start record offset. And then the end index will just be our start index, and then we will add the window record count. And that should make sense. We're going to go to the start of where we want to pull the records. We're going to add the number of records that equal the amount of time that we want to pull the data for, and that'll give us our window. So for our window, we'll take our transform data. We will start at the start record index, and we will just go to the end index. And then another thing that we want to do here is we want to remove this window from the data that we're going to be searching, so that we don't accidentally match against our window and actually just get back something indicating that we matched ourselves. So the search data is going to be the transform data starting at the beginning and going to the start record index. And then we're going to append to that the transformed data, and we're going to start at the end index, and then we'll go all the way to the end, which is specified by the -1. And what this does is basically cut the window that we're looking for out of the data we'll be searching. So we'll return the window and the search data, and I'll just use this here. And so inside the pattern finder, we'll say from extractor import get data window. We can remove this, and we will say window to match. You could also say pattern to match. Doesn't really matter. Would be get data window, and then we're going to pass in, obviously, our transformed data. We're going to pass in our window size in minutes. And the window size minutes is going to be minutes per record. Window size minutes is minutes per record, and we want to actually, let's get 3 hours. So basically, when we say minutes per record, which is going to be 60, and then we multiply that by 3, we're saying we want 180 minutes worth of data. The minutes per record is just going to be minutes per record, and then the offset from end. The offset from end is we're just going to take the last 3 hours. So we could say minutes per record, and we can multiply that by 6, and that would say go back 6 hours in the past and then give me a 3-hour window. We could say minutes per record times 12, go back 12 hours into the past and give me a 3-hour window. But we're just going to take the last 3 hours. So basically start at the end, go back 3 hours, give me all of that data. Because really when you're doing pattern recognition like this in a real-time system, what you're interested in is where am I now and what should I expect next. Okay, so that should give us our window to match. The next thing that we want to do is we want to actually find the closest match to this window. And so what I think I'm going to do is just create something called a finder. You could call it a comparer, you could call it a matcher. I'm going to call it a finder. We're going to use numpy and then we're also, this is where we're going to use the stumpy library that'll actually do the work of finding the patterns. I'm going to define one function, find closest matching window. In here we are going to pass in our search data. We're going to pass in the window to match. And remember at this point, this data is still multidimensional. So there's one axis for labels and one axis for values. If we wanted to make this more generic, we could pass in an index that tells us which of those dimensions is the data index. But since we didn't do it for cleaning, I'm not going to do it here, but you of course could. So in here, we're going to say the pattern to find. What we're going to do is split off the data from the labels. And as part of doing that, what we're going to need to do is convert these into NP arrays, because the search data in the window to match currently are lists, and if we try to index against them, it is going to fail. So we're going to say that the window to match, we're going to convert that to an NP array. We are going to slice off the first the first index, not the 0th, but the first, and then we're going to make sure it should already be a float. Doesn't hurt to convert it here. We're going to do the same thing with the values that we want to search. So values to search, same thing, convert it to an NP array so that we can index against it. We're going to take the same slice of it, and now we're going to, we got to define some variable pattern length, and this is just the length of the pattern to find. And we could, it's not length, it's just len. We could do this as we're passing it into the stump function that we're going to write in a second, but it's useful to have it as variable, one, because it's cleaner to look at, two, I think we're going to use it in another place. So now we're actually going to use Stumpy, and Stumpy is going to create something called a matrix profile for us. And the matrix profile has a lot of data in it, but the parts that we're going to care about are it's going to have a start index within our search data where it finds a match. And then we're going to use that to actually extract the match. And later on, we'll use that to look a little bit into the future of where the match was. So we're going to use the Stumpy library. It's got a method called stump, and it's got a couple of parameters. TA is just the name that it uses for the pattern we want to find. So we're going to pass that in. It's got a parameter M, which is our pattern length. It's got TB, which is the data we want to search. So we're going to say values to search there. It's got a parameter called ignore trivial, which we want to set to false. And then a normalize parameter, normalize, and we're going to set that to true. And what that'll do is take all of our ranges of values and pull them into the same range so that we get a better match and it's easier to search the data. So the matrix profile, if you're interested, you could print out the matrix profile. It has several pieces of information in there. It is a multi-dimensional array, and the thing that we care about is the second element of the first item in the array. So we're going to say the match start index is going to be matrix profile 0, 1. So again, it's multi-dimensional. We're going to take the first element and then take the second data piece out of there. That'll be our match start index. We're also going to meet our match end index. This is important not only for pulling out the window that we want to match, but also we're going to return this back to our pattern finder so that it can look a little bit into the future. And this is just the match start index plus the pattern length, because the match should be the same length as what we were looking for. We'll now pull out the matching window. The matching window will be our search data, and we'll go to the match start index, and then we'll take it until the match end index. And then we're just going to return all of this back to the pattern finder. So we will return the matching window, and we will return the match start index, and we will return the match end index. And that should be it for the finder. And so in here we're going to take this function, we're going to import it. So from finder, we're going to import find closest matching window. And so we're going to say matching window match start index and match end index equal find closest matching window. Into that we're going to pass our search data, and we're going to pass our window to match. And then I'm just going to print this matching window out just to make sure everything works. Matching window. I'll come down here and we'll say Python pattern finder.py. This can take a little bit the first time you run it. Once it does run it the first time, it gets increasingly faster. But I'll speed this up a little bit, and we'll take a look at the data once it's done processing it. Okay, and so what we find is we have a 3-hour window. We've gone back 3 hours, and this is the closest match. That's not all that interesting. Let's make this something like 24 hours. Let's look at the last 24 hours and see what that looks like. That's a little bit more interesting. That gives us some more data to look at. I think maybe what we want to do now is let's actually go into our plot, and let's let's do this. Let's say data. Let's turn this into a function so that we can also define a function that lets us print out the data that we have. And I probably need to actually define this correctly. There we go. Let's define print window, and we'll say window data as our input. For our window data, as you can see down here, it is an array of lists. And so what we'll want to do is say values np array window data, and then we will split off, yeah, we can do it here. We can do it in line. We'll split off the first element. We'll do it, make sure it's already a float in our data, but it doesn't hurt to ensure it, because you never know what people could pass in. And then we can just copy this. We don't need to rewrite it all from scratch. And make sure everything is aligned. And I think we actually might want to save this. So let's actually save this. So what we'll do is we'll say window data, and then give it a file name. And instead of show, we will say save fig, and we will give it the file name, and then that will save, and we'll be able to compare it side by side. And here we'll say print window, window to match, and we'll say the file name is window to match.png. Do the same thing. We'll say matching window, and then we'll pass in the matching window. Okay, there we go. We'll run that. All right, now we have an image of what we wanted to match, and let's pull that over here. Let's actually split this, and then we'll say matching window here. And so you'll see they're not exactly the same, but they are similar. And so close enough. You'll see a big dip here, little raise here that kind of correlates to this. This shape is different than this, but it's a similar enough pattern that it's interesting. So what I want to do now is let's look a little bit into the future, and let's get a window for the next 24 hours. So we've got a 24-hour match. Let's find the next 24 hours. So we're going to say future end index is the minimum of, we're going to take the match end index plus the minutes per record. And we're going to, again, do this for 24. So 24, that should be times 24, or the length of our search data. And we do this because we don't want to overrun the end of the array. And then we'll say the future is our search data, and we'll start at our match end index. This is the end of the matching window, and then we will go 24 hours into the future or to the end of the search data, whatever comes first. And then we will print window, the future, and we'll call it the future.png. And we'll run this again. Okay, we've got the future. And so this is the pattern that our matching algorithm tells us we should expect in the next 24 hours. Again, this is not deterministic. This should just